Chapter 1: An Introduction to Geology. All four of Earth's spheres are represented in this image in the Canadian Rockies of British Columbia. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 1.1 Distinguish between physical and historical geology and describe the connections between people and geology. 1.2 Summarize early and modern views on how change occurs on Earth and relate them to the prevailing ideas about the age of Earth. 1.3 Discuss the nature of scientific inquiry, including the construction of hypotheses and the development of theories. 1.4 List and describe Earth's four major spheres. Define system and explain why Earth is considered to be a system. 1.5 Outline the stages in the formation of our solar system. 1.6 Describe Earth's internal structure. 1.7 Sketch, label, and explain the rock cycle. 1.8 List and describe the major features of the continents and ocean basins. The spectacular eruption of a volcano, the terror brought by an earthquake, the magnificent scenery of a mountain range, and the destruction created by a landslide or flood are all subjects for a geologist. The study of geology deals with many fascinating and practical questions about our physical environment. What forces produce mountains? When will the next major earthquake occur in California? What are ice ages like, and will there be another? How were deposits formed? Where should we search for water? Will plentiful oil be found if a well is drilled in a particular location? Geologists seek to answer these and many other questions about Earth, its history, and its resources. 1.1 Geology, the science of Earth. Distinguish between physical and historical geology and describe the connections between people and geology. The subject of this text is geology, from the Greek geo and logos. Geology is the science that pursues an understanding of planet Earth. Understanding Earth is challenging because our planet is a dynamic body with many interacting parts and a complex history. Throughout its long existence, Earth has been changing. In fact, it is changing as you read this page and will continue to do so. Sometimes the changes are rapid and violent, as when landslides or volcanic eruptions occur. Just as often, change takes place so slowly that it goes unnoticed during a lifetime. Scales of size and space also vary greatly among the phenomena that geologists study. Sometimes geologists must focus on phenomena that are microscopic, such as the crystalline structure of minerals, and at other times they must deal with features that are continental or global in scale, such as the formation of major mountain ranges. Physical and historical geology. Geology is traditionally divided into two broad areas, physical and historical. Physical geology, which is the primary focus of this book, examines the materials composing Earth and seeks to understand the many processes that operate beneath and upon its surface. The aim of historical geology, on the other hand, is to understand the origin of Earth and its development through time. Thus, it strives to establish an orderly chronological arrangement of the multitude of physical and biological changes that have occurred in the geologic past. The study of physical geology logically precedes the study of Earth history because we must first understand how Earth works before we attempt to unravel its past. It should also be pointed out that physical and historical geology are divided into many areas of specialization. Every chapter of this book represents one or more areas of specialization in geology. The processes that operate beneath and upon Earth's surface are an important focus of physical geology. Figure 1.1 Internal and external processes. Figure 1.1 Full alternative text description. Geology is perceived as a science that is done outdoors, and rightly so. A great deal of geology is based on observations, measurements, and experiments conducted in the field. But geology is also done in the laboratory, where, for example, analysis of minerals and rocks provides insights into many basic processes, and the microscopic study of fossils unlocks clues to past environments. Geologists must also understand and apply knowledge and principles from physics, chemistry, and biology. Geology is a science that seeks to expand our knowledge of the natural world and our place in it. Geology involves not only outdoor fieldwork but work in the laboratory as well. This research team is gathering data at Mount Nyiragongo, an active volcano in the Democratic Republic of the Congo. Figure 1.2 in the field and in the lab. B. This researcher is using a petrographic microscope to study the mineral compositions of rock samples. Geology, people, and the environment. The primary focus of this book is to develop your understanding of basic geologic principles, but along the way we will explore numerous important relationships between people and the natural environment. Many of the problems and issues addressed by geology are of practical value to people. Natural hazards are a part of living on Earth. Every day they adversely affect millions of people worldwide and are responsible for staggering damages. Among the hazardous Earth processes that geologists study are volcanoes, floods, tsunamis, earthquakes, and landslides. Of course, geologic hazards are natural processes. They become hazards only when people try to live where these processes occur. During a 3-week span in spring 2015, the small Himalayan country of Nepal experienced 2 major earthquakes. There were more than 8,000 fatalities and nearly 500,000 homes destroyed. Geologic hazards are natural processes. They become hazards only when people try to live where these processes occur. The debris flow shown in Figure 1.15 and the volcanic eruption related to Figure 1.17 are also examples of geologic hazards that had deadly consequences. Figure 1.3 Earthquake destruction. Did you know? Each year an average American requires huge quantities of earth materials. Imagine receiving your annual share in a single delivery. A large truck would pull up to your home and unload 12,965 pounds of stone, 8,945 pounds of sand and gravel, 895 pounds of cement, 395 pounds of salt, 361 pounds of phosphate, and 974 pounds of other nonmetals. In addition, there would be 709 pounds of metals, including iron, aluminum, and copper. According to the United Nations, more people now live in cities than in rural areas. This global trend toward urbanization concentrates millions of people into megacities, many of which are vulnerable to natural hazards. Coastal sites are becoming more vulnerable because development often destroys natural defenses such as wetlands and sand dunes. In addition, there is a growing threat associated with human influences on the Earth system. One example is sea level rise that is linked to global climate change. Some mega cities are exposed to seismic and volcanic hazards, the threat of which may be compounded by inappropriate land use, poor construction practices, and rapid population growth. Resources are another important focus of geology that is of great practical value to people. Resources include water and soil, a great variety of metallic and nonmetallic minerals, and energy. Together they form the very foundation of modern civilization. Geology deals not only with the formation and occurrence of these vital resources but also with maintaining supplies and with the environmental impact of their extraction and use. Mineral and energy resources represent an important link between people and geology. This large open-pit mine is in Arizona. Figure 1.4 Copper mining. Did you know? It took until about the year 1800 for the world population to reach 1 billion. By 1927, the number had doubled to 2 billion. According to United Nations estimates, world population reached 7 billion in late October 2011. We are currently adding about 80 million people per year to the planet. Geologic processes clearly have an impact on people. In addition, we humans can dramatically influence geologic processes. For example, landslides and river flooding occur naturally, but the magnitude and frequency of these processes can be affected significantly by human activities such as clearing forests, building cities, and constructing dams. Unfortunately, natural systems do not always adjust to artificial changes in ways that we can anticipate. Thus, an alteration to the environment that was intended to benefit society sometimes has the opposite effect. At appropriate places throughout this textbook, you will have opportunities to examine different aspects of our relationship with the physical environment. Nearly every chapter addresses some aspect of natural hazards, resources, and the environmental issues associated with each. Significant parts of some chapters provide the basic geologic knowledge and principles needed to understand environmental problems. Concept checks 1.1. 1. Name and distinguish between the two broad subdivisions of geology. 2. List at least 3 different geologic hazards. 3. Aside from geologic hazards, describe another important connection between people and geology. 1.2 The development of geology. Summarize early and modern views on how change occurs on Earth and relate them to the prevailing ideas about the age of Earth. The nature of our Earth, its materials and processes, has been a focus of study for centuries. Writings about such topics as fossils, gems, earthquakes, and volcanoes date back to the early Greeks, more than 2,300 years ago. The Greek philosopher Aristotle strongly influenced later Western thinking. Unfortunately, Aristotle's explanations about the natural world were not based on keen observations and experiments. He arbitrarily stated that rocks were created under the influence of the stars and that earthquakes occurred when air crowded into the ground, was heated by central fires, and escaped explosively. When confronted with a fossil fish, he explained that a great many fishes live in the earth motionless and are found when excavations are made. Although Aristotle's explanations may have been adequate for his day, they unfortunately continued to be viewed as authoritative for many centuries, thus inhibiting the acceptance of more up-to-date ideas. After the Renaissance of the 1500s, however, more people became interested in finding answers to questions about Earth. Catastrophism. In the mid-1600s, James Ussher, Anglican Archbishop of Armagh, Primate of all Ireland, published a major work that had immediate and profound influences. A respected scholar of the Bible, Ussher constructed a chronology of human and Earth history in which he calculated that Earth was only a few thousand years old, having been created in 4004. Ussher's treatise earned widespread acceptance among Europe's scientific and religious leaders, and his chronology was soon printed in the margins of the Bible itself. During the 17th and 18th centuries, Western thought about Earth's features and processes was strongly influenced by Ussher's calculation. The result was a guiding doctrine called catastrophism. Catastrophists believed that Earth's landscapes were shaped primarily by great catastrophes. Features such as mountains and canyons, which today we know take great spans of time to form, were explained as resulting from sudden and often worldwide disasters produced by unknowable causes that no longer operate. This philosophy was an attempt to fit the rates of Earth processes to the then current ideas about the age of Earth. The birth of modern geology. Against the backdrop of Aristotle's views and the idea of an Earth created in 4004, a Scottish physician and gentleman farmer named James Hutton published Theory of the Earth in 1795. In this work, Hutton put forth a fundamental principle that is a pillar of geology today: uniformitarianism. It states that the physical, chemical, and biological laws that operate today have also operated in the geologic past. This means that the forces and processes that we observe presently shaping our planet have been at work for a very long time. Thus, to understand ancient rocks, we must first understand present-day processes and their results. This idea is commonly stated as the present is the key to the past. Prior to Hutton's theory of the Earth, no one had effectively demonstrated that geologic processes occur over extremely long periods of time. However, Hutton persuasively argued that forces that appear small can, over long spans of time, produce effects that are just as great as those resulting from sudden catastrophic events. Unlike his predecessors, Hutton carefully cited verifiable observations to support his ideas. For example, when Hutton argued that mountains are sculpted and ultimately destroyed by weathering and the work of running water and that the products are carried to the oceans by observable processes, he said, "We have a chain of facts which clearly demonstrate that the materials of the wasted mountains have traveled through the rivers, and further, there is not one step in all this progress that is not to be actually perceived." He then went on to summarize this thought by asking a question and immediately providing the answer: what more can we require? Nothing but time. Geology today. Today the basic tenets of uniformitarianism are just as viable as in Hutton's day. Indeed, today we realize more strongly than ever before that the present gives us insight into the past and that the physical, chemical, and biological laws that govern geologic processes remain unchanging through time. However, we also understand that the doctrine should not be taken too literally. To say that geologic processes in the past were the same as those occurring today is not to suggest that they have always had the same relative importance or that they have operated at precisely the same rate. Moreover, some important geologic processes are not currently observable, but evidence that they occur is well established. For example, we know that impacts from large meteorites have altered Earth's climate and influenced the history of life, even though we have no historical accounts of such impacts. Did you know? Shortly after Archbishop Usher determined an age for Earth, another biblical scholar, Dr. John Lightfoot of Cambridge, felt he could be even more specific. He wrote that Earth was created on the 26th of October 4004 BC at 9 o'clock in the morning. The acceptance of uniformitarianism meant the acceptance of a very long history for Earth. Although Earth processes vary in intensity, they almost always take a very long time to create or destroy major landscape features. The Grand Canyon provides a good example. The Grand Canyon of the Colorado River in northern Arizona. Smart Figure 1.5 Earth History, written in the rocks. Watch Mobile Field Trip, a geologist's Grand Canyon. The rock record contains evidence which shows that Earth has experienced many cycles of mountain building and erosion. Concerning the ever-changing nature of Earth through great expanses of geologic time, Hutton famously stated in 1788, "The results, therefore, of our present inquiry is, that we find no vestige of a beginning, no prospect of an end." In the chapters that follow, we will be examining the materials that compose our planet and the processes that modify it. It is important to remember that, although many features of our physical landscape may seem to be unchanging over the decades we observe them, they are nevertheless changing, but on time scales of hundreds, thousands, or even many millions of years. The magnitude of geologic time. Among geology's important contributions to human knowledge is the discovery that Earth has a very long and complex history. Although James Hutton and others recognized that geologic time is exceedingly long, they had no methods to accurately determine the age of Earth. Early time scales simply placed the events of Earth history in the proper sequence or order, without knowledge of how long ago in years they occurred. Today our understanding of radioactivity allows us to accurately determine numerical dates for rocks that represent important events in Earth's distant past. For example, we know that the dinosaurs died out about 66 million years ago. Today the age of Earth is put at about 4.6 billion years. Chapter 18 is devoted to a much more complete discussion of geologic time and the geologic time scale. The time scale divides the vast 4.6 billion year history of Earth into eons, eras, periods, and epochs. Numbers on the time scale represent time in millions of years before the present. The Precambrian accounts for more than 88% of geologic time. The geologic time scale is a dynamic tool that is periodically updated. Numerical ages appearing on this time scale are those that were currently accepted by the International Commission on Stratigraphy in 2015. The color scheme used on this chart was selected because it is similar to that used by the ICS. The ICS is responsible for establishing global standards for the time scale. Figure 1.6 Geologic Time Scale, a basic reference. Figure 1.6 Full alternative text description. The concept of geologic time is new to many non-geologists. People are accustomed to dealing with increments of time that are measured in hours, days, weeks, and years. Our history books often examine events over spans of centuries, but even a century is difficult to appreciate fully. For most of us, someone or something that is 90 years old is very old, and a 1,000-year-old artifact is ancient. By contrast, those who study geology must routinely deal with vast time periods, millions or billions of years. When viewed in the context of Earth's 4.6 billion-year history, a geologic event that occurred 100 million years ago may be characterized as recent by a geologist, and a rock sample that has been dated at 10 million years may be called young. An appreciation for the magnitude of geologic time is important in the study of geology because many processes are so gradual that vast spans of time are needed before significant changes occur. How long is 4.6 billion years? If you were to begin counting at the rate of 1 number per second and continued 24 hours a day, 7 days a week and never stopped, it would take about 2 lifetimes to reach 4.6 billion. Figure 1.7 provides another interesting way of viewing the expanse of geologic time. This is just one of many analogies that have been conceived in an attempt to convey the magnitude of geologic time. Although helpful, all of them, no matter how clever, only begin to help us comprehend the vast expanse of Earth history. Smart Figure 1.7 Magnitude of geologic time. Smart Figure 1.7 Full alternative text description. Watch tutorial, Geologic time. Concept checks 1.2. 1. Describe Aristotle's influence on geology. 2. Contrast catastrophism and uniformitarianism. How did each view the age of Earth? 3. How old is Earth? 4. Refer to Figure 1.6 and list the eon, era, period, and epoch in which we live. 1.3 The nature of scientific inquiry. Discuss the nature of scientific inquiry, including the construction of hypotheses and the development of theories. In our modern society, we are constantly reminded of the benefits derived from science. But what exactly is the nature of scientific inquiry? Science is a process of producing knowledge, based on making careful observations and on creating explanations that make sense of the observations. Developing an understanding of how science is done and how scientists work is an important theme that appears throughout this textbook. You will explore the difficulties in gathering data and some of the ingenious methods that have been developed to overcome these difficulties. You will also see many examples of how hypotheses are formulated and tested, and you will learn about the evolution and development of some major scientific theories. All science is based on the assumption that the natural world behaves in a consistent and predictable manner that is comprehensible through careful, systematic study. The overall goal of science is to discover the underlying patterns in nature and then to use that knowledge to make predictions about what should or should not be expected, given certain facts or circumstances. For example, by knowing how oil deposits form, geologists are able to predict the most favorable sites for exploration and, perhaps as importantly, how to avoid regions that have little or no potential. The development of new scientific knowledge involves some basic logical processes that are universally accepted. To determine what is occurring in the natural world, scientists collect data through observation and measurement. The data collected often help answer well-defined questions about the natural world. Because some error is inevitable, the accuracy of a particular measurement or observation is always open to question. Nevertheless, these data are essential to science and serve as a springboard for the development of scientific theories. Scientific facts are gathered in many ways. Figure 1.8 Observation and Measurement. Figure 1.8 Full alternative text description. Hypothesis. Once data have been gathered and principles have been formulated to describe a natural phenomenon, investigators try to explain how or why things happen in the manner observed. They often do this by constructing a tentative explanation, which is called a scientific hypothesis. It is best if an investigator can formulate more than one hypothesis to explain a given set of observations. If an individual scientist is unable to devise multiple hypotheses, others in the scientific community will almost always develop alternative explanations. A spirited debate frequently ensues. As a result, extensive research is conducted by proponents of opposing hypotheses, and the results are made available to the wider scientific community in scientific journals. Before a hypothesis can become an accepted part of scientific knowledge, it must pass objective testing and analysis. If a hypothesis cannot be tested, it is not scientifically useful, no matter how interesting it might seem. The verification process requires that predictions be made, based on the hypothesis being considered, and that the predictions be tested through comparison against objective observations of nature. Put another way, hypotheses must fit observations other than those used to formulate them in the first place. Hypotheses that fail rigorous testing are ultimately discarded. The history of science is littered with discarded hypotheses. One of the best known is the Earth-centered model of the universe, a proposal that was supported by the apparent daily motion of the Sun, Moon, and stars around Earth. As the mathematician Jacob Bronowski so ably stated, science is a great many things. But in the end they all return to this: science is the acceptance of what works and the rejection of what does not. Theory. When a hypothesis has survived extensive scrutiny and when competing hypotheses have been eliminated, a hypothesis may be elevated to the status of a scientific theory. In everyday speech, we frequently hear people say, "That's only a theory," implying that a theory is an educated guess or hypothesis. But to a scientist, a theory is a well-tested and widely accepted view that the scientific community agrees best explains certain observable facts. Some theories that are extensively documented and extremely well supported are comprehensive in scope. For example, the theory of plate tectonics provides a framework for understanding the origins of mountains, earthquakes, and volcanic activity. In addition, plate tectonics explains the evolution of the continents and the ocean basins through time, ideas that are explored in some detail in chapters 2, 10, and 11. Scientific methods. The process just described, in which researchers gather facts through observations and formulate scientific hypotheses, is called the scientific method. Contrary to popular belief, the scientific method is not a standard recipe that scientists apply in a routine manner to unravel the secrets of our natural world. Rather, it is an endeavor that involves creativity and insight. Rutherford and Algren put it this way: inventing hypotheses or theories to imagine how the world works and then figuring out how they can be put to the test of reality is as creative as writing poetry, composing music, or designing skyscrapers. There is no fixed path that scientists always follow that leads unerringly to scientific knowledge. However, many scientific investigations involve the steps outlined in Figure 1.9. In addition, some scientific discoveries result from purely theoretical ideas that stand up to extensive examination. Some researchers use high-speed computers to create models that simulate what is happening in the real world. These models are useful when dealing with natural processes that occur on very long time scales or take place in extreme or inaccessible locations. Still other scientific advancements are made when a totally unexpected happening occurs during an experiment. These serendipitous discoveries are more than pure luck, for as the 19th-century French scientist Louis Pasteur said, in the field of observation, chance favors only the prepared mind. The diagram depicts the steps involved in the process many refer to as the scientific method. Figure 1.9 Steps frequently followed in scientific investigations. Figure 1.9 Full alternative text description. Did you know? A scientific law is a basic principle that describes a particular behavior of nature that is generally narrow in scope and can be stated briefly, often as a simple mathematical equation. Scientific knowledge is acquired through several avenues, so it might be best to describe the nature of scientific inquiry as the methods of science rather than as the scientific method. In addition, it should always be remembered that even the most compelling scientific theories are still simplified explanations of the natural world. Plate tectonics and scientific inquiry. This textbook offers many opportunities to develop and reinforce your understanding of how science works and, in particular, how the science of geology works. You will learn about data-gathering methods and the observational techniques and reasoning processes used by geologists. Chapter 2 provides an excellent example. Over the past 50 years, we have learned a great deal about the workings of our dynamic planet. This period has seen an unequaled revolution in our understanding of Earth. The revolution began in the early part of the 20th century, with the radical proposal of continental drift, the idea that the continents move about the face of the planet. This hypothesis contradicted the established view that the continents and ocean basins are permanent and stationary features on the face of Earth. For that reason, the notion of drifting continents was received with great skepticism and even ridicule. More than 50 years passed before enough data were gathered to transform this controversial hypothesis into a sound theory that wove together the basic processes known to operate on Earth. The theory that finally emerged, called the theory of plate tectonics, provided geologists with the first comprehensive model of Earth's internal workings. In Chapter 2, you will not only gain insights into the workings of our planet but also see an excellent example of the way geologic truths are uncovered and reworked. Concept checks 1.3. 1. How is a scientific hypothesis different from a scientific theory? 2. Summarize the basic steps followed in many scientific investigations. F. James Rutherford and Andrew Algren, Science for All Americans, page 7. 1.4 Earth as a system. List and describe Earth's four major spheres. Define system and explain why Earth is considered to be a system. Anyone who studies Earth soon learns that our planet is a dynamic body with many separate but interacting parts, or spheres. The hydrosphere, atmosphere, biosphere, and geosphere and all of their components can be studied separately. However, the parts are not isolated. Each is related in some way to the others, producing a complex and continuously interacting whole that we call the Earth system. Earth spheres. The images in Figure 1.10 are considered to be classics because they let humanity see Earth differently than ever before. These early views profoundly altered our conceptualizations of Earth and remain powerful images decades after they were first viewed. Seen from space, Earth is breathtaking in its beauty and startling in its solitude. The photos remind us that our home is, after all, a planet, small, self-contained, and in some ways even fragile. The accompanying video commemorates the 45th anniversary of Apollo 8's historic flight by recreating the moment when the crew first saw and photographed the Earth rising from behind the Moon. Smart Figure 1.102 Classic Views of Earth from Space. Smart Figure 1.10 Full alternative text description. As we look closely at our planet from space, it becomes apparent that Earth is much more than rock and soil. In fact, the most conspicuous features of Earth in Figure 1.10a are swirling clouds suspended above the surface of the vast global ocean. These features emphasize the importance of water on our planet. Did you know? The volume of ocean water is so large that if Earth's solid mass were perfectly smooth and spherical, the oceans would cover Earth's entire surface to a uniform depth of more than 2,000 m. The closer view of Earth from space shown in Figure 1.10b helps us appreciate why the physical environment is traditionally divided into three major parts: the water portion of our planet, the hydrosphere, Earth's gaseous envelope, the atmosphere, and, of course, the solid Earth, or geosphere. It needs to be emphasized that our environment is highly integrated and not dominated by rock, water, or air alone. Rather, it is characterized by continuous interactions as air comes in contact with rock, rock with water, and water with air. Moreover, the biosphere, which is the totality of all life on our planet, interacts with each of the three physical realms and is an equally integral part of the planet. Thus, Earth can be thought of as consisting of four major spheres: the hydrosphere, atmosphere, geosphere, and biosphere. All four spheres are represented in the chapter opening photo. The interactions among Earth's spheres are incalculable. Figure 1.11 provides us with one easy-to-visualize example. The shoreline is an obvious meeting place for rock, water, and air. In this scene, ocean waves created by the drag of air moving across the water are breaking against the rocky shore. The shoreline is one obvious interface, a common boundary where different parts of a system interact. In this scene, ocean waves that were created by the force of moving air break against a rocky shore. The force of the water can be powerful, and the erosional work that is accomplished can be great. Figure 1.11 Interactions among Earth's spheres. Hydrosphere. Earth is sometimes called the blue planet. Water, more than anything else, makes Earth unique. The hydrosphere is a dynamic mass of water that is continually on the move, evaporating from the oceans to the atmosphere, precipitating to the land, and running back to the ocean again. The global ocean is certainly the most prominent feature of the hydrosphere, blanketing nearly 71% of Earth's surface to an average depth of about 3,800 meters. It accounts for about 97% of Earth's water. However, the hydrosphere also includes the freshwater found underground and in streams, lakes, and glaciers. Moreover, water is an important component of all living things. Distribution of water in the hydrosphere. Figure 1.12 Full alternative text description. Even though freshwater constitutes only a small fraction of Earth's hydrosphere, it plays an outsized role in Earth's external processes. Streams, glaciers, and groundwater sculpt many of our planet's varied landforms, and freshwater is vital for life on land. Atmosphere. Figure 1.12 The water planet. Earth is surrounded by a life-giving gaseous envelope called the atmosphere. When we watch a high-flying jet plane cross the sky, it seems that the atmosphere extends upward for a great distance. However, when compared to the thickness of the solid Earth, about 6,400 kilometers, the atmosphere is a very shallow layer. Despite its modest dimensions, this thin blanket of air is an integral part of the planet. It not only provides the air we breathe but also protects us from the sun's intense heat and dangerous ultraviolet radiation. The energy exchanges that continually occur between the atmosphere and Earth's surface and between the atmosphere and space produce the effects we call weather and climate. Climate has a strong influence on the nature and intensity of Earth's external processes. When climate changes, these processes respond. The atmosphere is an integral part of the planet. Figure 1.13 A shallow layer. Figure 1.13 Full alternative text description. If, like the Moon, Earth had no atmosphere, our planet would be lifeless, and many of the processes and interactions that make the surface such a dynamic place could not operate. Without weathering and erosion, the face of our planet might more closely resemble the lunar surface, which has not changed appreciably in nearly 3 billion years. Biosphere. The biosphere includes all life on Earth. Ocean life is concentrated in the sunlit upper waters. Most life on land is also concentrated near the surface, with tree roots and burrowing animals reaching a few meters underground and flying insects and birds reaching a kilometer or so into the atmosphere. A surprising variety of life forms are also adapted to extreme environments. For example, on the ocean floor, where pressures are extreme and no light penetrates, there are places where vents spew hot, mineral-rich fluids that support communities of exotic life forms. On land, some bacteria thrive in rocks as deep as 4 kilometers and in boiling hot springs. Moreover, air currents can carry microorganisms many kilometers into the atmosphere. But even when we consider these extremes, life still must be thought of as being confined to a narrow band very near Earth's surface. The biosphere, one of Earth's 4 spheres, includes all life. A. Tropical rainforests are teeming with life and occur in the vicinity of the equator. B. Some life is found in extreme environments such as the absolute darkness of the deep ocean. Figure 1.14 The biosphere. Figure 1.14 Full alternative text description. Did you know? Primitive life first appeared in the oceans about 4 billion years ago and has been spreading and diversifying ever since. Plants and animals depend on the physical environment for the basics of life. However, organisms do not just respond to their physical environment. Through countless interactions, life forms help maintain and alter the physical environment. Without life, the makeup and nature of the geosphere, hydrosphere, and atmosphere would be very different. Geosphere. Lying beneath the atmosphere and the oceans is the solid Earth, or geosphere. The geosphere extends from the surface to the center of the planet, a depth of nearly 6,400 kilometers, making it by far the largest of Earth's 4 spheres. Much of our study of the solid Earth focuses on the more accessible surface features. Fortunately, many of these features represent the outward expressions of the dynamic behavior of Earth's interior. By examining the most prominent surface features and their global extent, we can obtain clues to the dynamic processes that have shaped our planet. A first look at the structure of Earth's interior and at the major surface features of the geosphere will come later in the chapter. Soil, the thin veneer of material at Earth's surface that supports the growth of plants, may be thought of as part of all 4 spheres. The solid portion is a mixture of weathered rock debris and organic matter from decayed plant and animal life. The decomposed and disintegrated rock debris is the product of weathering processes that require air and water. Air and water also occupy the open spaces between the solid particles. Anyone who studies Earth soon learns that our planet is a dynamic body with many separate but interacting parts, or spheres. The hydrosphere, atmosphere, biosphere, and geosphere and all of their components can be studied separately. However, the parts are not isolated. Each is related in some way to the others, producing a complex and continuously interacting whole that we call the Earth system. Earth system science. A simple example of the interactions among different parts of the Earth system occurs every winter, as moisture evaporates from the Pacific Ocean and subsequently falls as rain in the mountains of Washington, Oregon, and California, triggering destructive debris flows. The processes that move water from the hydrosphere to the atmosphere and then to the solid Earth have a profound impact on the plants and animals that inhabit the affected regions. This image provides an example of interactions among different parts of the Earth system. Extraordinary rains triggered this debris flow on March 22, 2014, near Oso, Washington. The mass of mud and debris blocked the North Fork of the Stillaguamish River and engulfed an area of about 2.6 square kilometers. 43 people perished. Figure 1.15 Deadly debris flow. Did you know? Since 1970, Earth's average surface temperature has increased by about 0.6 C. By the end of the 21st century, the average global temperature may increase by an additional 2 to 4.5 C. Scientists have recognized that in order to more fully understand our planet, they must learn how its individual components are interconnected. This endeavor, called Earth System Science, aims to study Earth as a system composed of numerous interacting parts, or subsystems. Rather than look through the limited lens of only one of the traditional sciences, geology, atmospheric science, chemistry, biology, and so on, Earth System Science attempts to integrate the knowledge of several academic fields. Using an interdisciplinary approach, those engaged in Earth System Science attempt to achieve the level of understanding necessary to comprehend and solve many of our global environmental problems. A system is a group of interacting, or interdependent, parts that form a complex whole. Most of us hear and use the term system frequently. We may service our car's cooling system, make use of the city's transportation system, and be a participant in the political system. A news report might inform us of an approaching weather system. Further, we know that Earth is just a small part of a larger system known as the solar system, which in turn is a subsystem of an even larger system called the Milky Way galaxy. The Earth System. The Earth system has a nearly endless array of subsystems in which matter is recycled over and over. One familiar loop or subsystem is the hydrologic cycle. It represents the unending circulation of Earth's water among the hydrosphere, atmosphere, biosphere, and geosphere. Water enters the atmosphere during volcanic eruptions and through evaporation from Earth's surface and transpiration from plants. Water vapor condenses in the atmosphere to form clouds, which in turn produce precipitation that falls back to Earth's surface. Some of the rain that falls onto the land infiltrates and is taken up by plants or becomes groundwater, and some flows across the surface toward the ocean. Water readily changes state from liquid to gas to solid at the temperatures and pressures occurring on Earth. This cycle traces the movements of water among Earth's four spheres. It is one of many subsystems that collectively make up the Earth system. Figure 1.16 The hydrologic cycle. Figure 1.16 Full alternative text description. Viewed over long time spans, the rocks of the geosphere are constantly forming, changing, and reforming. The loop that involves the processes by which one rock changes to another is called the rock cycle and will be discussed at some length later in the chapter. The cycles of the Earth system are not independent, to the contrary, these cycles come in contact and interact in many places. The parts of the Earth system are linked so that a change in one part can produce changes in any or all of the other parts. For example, when a volcano erupts, lava from Earth's interior may flow out at the surface and block a nearby valley. This new obstruction influences the region's drainage system by creating a lake or causing streams to change course. The large quantities of volcanic ash and gases that can be emitted during an eruption alter the composition of the atmosphere and influence the amount of solar energy that reaches Earth's surface. The result could be a drop in air temperatures over the entire hemisphere. Where the surface is covered by lava flows or a thick layer of volcanic ash, existing soils are buried. This causes the soil-forming processes to begin anew to transform the new surface material into soil. The soil that eventually forms will reflect the interactions among many parts of the Earth system, the volcanic parent material, the climate, and the impact of biological activity. Of course, there would also be significant changes in the biosphere. Some organisms and their habitats would be eliminated by the lava and ash, whereas new settings for life, such as a lake formed by a lava dam, would be created. The potential climate change could also impact sensitive life forms. When Mount St. Helens, Washington, erupted in May 1980, the area shown here was buried by a volcanic mudflow. Now plants are re-established, and new soil is forming. The Earth system is characterized by processes that vary on spatial scales from fractions of millimeters to thousands of kilometers. Time scales for Earth's processes range from milliseconds to billions of years. As we learn about Earth, it becomes increasingly clear that despite significant separations in distance or time, many processes are connected, and a change in one component can influence the entire system. Figure 1.17 Change is a geologic constant. The Earth system is powered by energy from two sources. The Sun drives external processes that occur in the atmosphere, in the hydrosphere, and at Earth's surface. Weather and climate, ocean circulation, and erosional processes are driven by energy from the Sun. Earth's interior is the second source of energy. Heat remaining from when our planet formed and heat that is continuously generated by radioactive decay power the internal processes that produce volcanoes, earthquakes, and mountains. Did you know? Estimates indicate that erosional processes are lowering the North American continent at a rate of about 3 centimeters per 1,000 years. At this rate, it would take 100 million years to level a 3,000 m high peak. Humans are part of the Earth system, a system in which the living and non-living components are entwined and interconnected. Therefore, our actions produce changes in all the other parts. When we burn gasoline and coal, dispose of our wastes, and clear the land, we cause other parts of the system to respond, often in unforeseen ways. Throughout this textbook you will learn about many of Earth's subsystems, including the hydrologic system, the tectonic system, the rock cycle, and the climate system. Remember that these components and we humans are all part of the complex interacting whole we call the Earth system. Concept checks 1.4. 1. List and briefly describe the 4 spheres that constitute the Earth system. 2. Compare the height of the atmosphere to the thickness of the geosphere. 3. How much of Earth's surface do oceans cover? What percentage of Earth's water supply do oceans represent? 4. What is a system? List 3 examples. 5. What are the 2 sources of energy for the Earth system? 1.5 Origin and early evolution of Earth. Outline the stages in the formation of our solar system. Recent earthquakes caused by displacements of Earth's crust and lavas spewed from active volcanoes represent only the latest in a long line of events by which our planet has attained its present form and structure. The geologic processes operating in Earth's interior can be best understood when viewed in the context of much earlier events in Earth history. Origin of planet Earth. This section describes the most widely accepted views on the origin of our solar system. The theory described here represents the most consistent set of ideas we have to explain what we know about our solar system today. The universe begins. Our scenario begins about 13.7 billion years ago, with the Big Bang, an almost incomprehensible event in which space itself, along with all the matter and energy of the universe, exploded in an instant from tiny to huge dimensions. As the universe continued to expand, subatomic particles condensed to form hydrogen and helium gas, which later cooled and clumped to form the first stars and galaxies. It was in one of these galaxies, the Milky Way, that our solar system, including planet Earth, took form. Did you know? The circumference of Earth is slightly more than 40,000 kilometers. It would take a jet plane traveling at 1,000 kilometers hr 40 hours to circle the planet. The solar system forms. Earth is one of 8 planets that, along with dozens of moons and numerous smaller bodies, revolve around the Sun. The orderly nature of our solar system helped scientists determine that Earth and the other planets formed at essentially the same time and from the same primordial material as the Sun. The nebular theory proposes that the bodies of our solar system evolved from an enormous rotating cloud called the solar nebula. Besides the hydrogen and helium atoms generated during the Big Bang, the solar nebula consisted of microscopic dust grains and other matter ejected ultimately from long-dead stars. The nebular theory explains the formation of the solar system. Smart Figure 1.18 Nebular Theory. Smart Figure 1.18 Full Alternative Text Description Watch Tutorial, The Nebular Theory. Nearly 5 billion years ago, something, perhaps a shock wave from an exploding star, caused this nebula to start collapsing in response to its own gravitation. As it collapsed, it evolved from a huge, vaguely rotating cloud to a much smaller, fast-spinning disk. The cloud flattened into a disk for the same reason that it is easier to move along with a crowd of circling ice skaters than to cross their path. The orbital plane within the cloud that started out with the largest amount of matter gradually, through collisions and other interactions, incorporated gas and particles that originally had other orbits until all the matter orbited in one plane. The disk spun faster as it shrank for the same reason ice skaters spin faster when they draw their arms toward their bodies. Most of the cloud's matter ended up in the center of the disk, where it formed the protoson. Astronomers have observed many such disks around newborn stars in neighboring regions of our galaxy. The protoson and inner disk were heated by the gravitational energy of infalling matter. In the inner disk, temperatures became high enough to cause the dust grains to evaporate. However, at distances beyond the orbit of Mars, the temperatures probably remained quite low. At 200 degrees Celsius. The tiny particles in the outer portion of the nebula were likely covered with a thick layer of frozen water, carbon dioxide, ammonia, and methane. The disk also contained appreciable amounts of the lighter gases hydrogen and helium. The inner planets form. The formation of the Sun marked the end of the period of contraction and thus the end of gravitational heating. Temperatures in the region where the inner planets now reside began to decline. The decrease in temperature caused those substances with high melting points to condense into tiny particles that began to coalesce. Materials such as iron and nickel and the elements of which the rock-forming minerals are composed, silicon, calcium, sodium, and so forth, formed metallic and rocky clumps that orbited the Sun. Repeated collisions caused these masses to coalesce into larger asteroid-sized bodies, called planetesimals, which in a few tens of millions of years accreted into the four inner planets we call Mercury, Venus, Earth, and Mars. Not all of these clumps of matter were incorporated into the planetesimals. Those rocky and metallic pieces that remained in orbit are called meteorites when they survive an impact with Earth. This image of asteroid 21 Lutetia was obtained by special cameras aboard the Rosetta spacecraft on July 10, 2010. Spacecraft instruments showed that Lutetia is a primitive body left over from when the solar system formed. Figure 1.19 A remnant planetesimal. As more and more material was swept up by the planets, the high-velocity impact of nebular debris caused the temperatures of these bodies to rise. Because of their relatively high temperatures and weak gravitational fields, the inner planets were unable to accumulate much of the lighter components of the nebular cloud. The lightest of these, hydrogen and helium, were eventually whisked from the inner solar system by the solar wind. Did you know? The Sun contains 99.86% of the mass of the solar system. The circumference of the Sun is 109 times that of Earth. A jet plane traveling at 1,000 km/h would require nearly 182 days to circle the Sun. The outer planets develop. At the same time that the inner planets were forming, the larger, outer planets, along with their extensive satellite systems, were also developing. Because of low temperatures far from the Sun, the material from which these planets formed contained a high percentage of ices, water, carbon dioxide, ammonia, and methane, as well as rocky and metallic debris. The accumulation of ices accounts, in part, for the large size and low density of the outer planets. The two most massive planets, Jupiter and Saturn, had a surface gravity sufficient to attract and hold large quantities of even the lightest elements, hydrogen and helium. Formation of Earth's layered structure. As material accumulated to form Earth, the high-velocity impact of nebular debris and the decay of radioactive elements caused the temperature of our planet to increase steadily. During this time of intense heating, Earth became hot enough that iron and nickel began to melt. Melting produced liquid blobs of dense metal that sank toward the center of the planet. This process occurred rapidly on the scale of geologic time and produced Earth's dense iron-rich core. Chemical differentiation and Earth's layers. The early period of heating resulted in another process of chemical differentiation, whereby melting formed buoyant masses of molten rock that rose toward the surface, where they solidified to produce a primitive crust. These rocky materials were enriched in oxygen and oxygen-seeking elements, particularly silicon and aluminum, along with lesser amounts of calcium, sodium, potassium, iron, and magnesium. In addition, some heavy metals such as gold, lead, and uranium, which have low melting points or were highly soluble in the ascending molten masses, were scavenged from Earth's interior and concentrated in the developing crust. This early period of chemical differentiation established the three basic divisions of Earth's interior: the iron-rich core, the thin primitive crust, and Earth's largest layer, called the mantle, which is located between the core and crust. An atmosphere develops. An important consequence of the early period of chemical differentiation is that large quantities of gaseous materials were allowed to escape from Earth's interior, as happens today during volcanic eruptions. By this process, a primitive atmosphere gradually evolved. It is on this planet, with this atmosphere, that life as we know it came into existence. Continents and ocean basins evolve. Following the events that established Earth's basic structure, the primitive crust was lost to erosion and other geologic processes, so we have no direct record of its makeup. When and exactly how the continental crust, and thus Earth's first land masses, came into existence is a matter of ongoing research. Nevertheless, there is general agreement that the continental crust formed gradually over the past 4 billion years. In addition, as you will see in subsequent chapters, Earth is an evolving planet whose continents and ocean basins have continually changed shape and even location. Did you know? The light year is a unit for measuring distances to stars. Such distances are so large that familiar units such as kilometers or miles are cumbersome to use. 1 light year is the distance light travels in 1 Earth year, about 9.5 trillion kilometers. Concept checks 1.5. 1. Name and briefly outline the theory that describes the formation of our solar system. 2. List the inner planets and outer planets. Describe basic differences in size and composition. 3. Explain why density and buoyancy were important in the development of Earth's layered structure. 1.6 Earth's internal structure. Describe Earth's internal structure. In the preceding section, you learned that the differentiation of material that began early in Earth's history resulted in the formation of 3 major layers defined by their chemical composition: the crust, mantle, and core. In addition to these compositionally distinct layers, Earth is divided into layers based on physical properties. The physical properties used to define such zones include whether the layer is solid or liquid and how weak or strong it is. Important examples include the lithosphere, asthenosphere, outer core, and inner core. Knowledge of both chemical and physical layers is important to our understanding of many geologic processes, including volcanism, earthquakes, and mountain building. Figure 1.20 shows different views of Earth's layered structure. Smart Figure 1.20 Earth's layers. Structure of Earth's interior, based on chemical composition and physical properties. Smart Figure 1.20 Full alternative text description. Watch tutorial, Earth's layers. Earth's crust. The crust, Earth's relatively thin, rocky outer skin, is of 2 different types, continental crust and oceanic crust. Both share the word crust, but the similarity ends there. The oceanic crust is roughly 7 kilometers thick and composed of the dark igneous rock basalt. By contrast, the The continental crust averages about 35 kilometers thick but may exceed 70 kilometers in some mountainous regions such as the Rockies and Himalayas. Unlike the oceanic crust, which has a relatively homogeneous chemical composition, the continental crust consists of many rock types. Although the upper crust has an average composition of a granitic rock called granodiorite, it varies considerably from place to place. Continental rocks have an average density of about 2.7 gcm3, and some have been discovered that are more than 4 billion years old. The rocks of the oceanic crust are younger and denser than continental rocks. For comparison, liquid water has a density of 1 gcm3, therefore, the density of basalt, the primary rock composing oceanic crust, is 3 times that of water. Earth's mantle. More than 82% of Earth's volume is contained in the mantle, a solid, rocky shell that extends to a depth of about 2,900 kilometers. The boundary between the crust and mantle represents a marked change in chemical composition. The dominant rock type in the uppermost mantle is peridotite, which is richer in the metals magnesium and iron than the minerals found in either the continental or oceanic crust. The upper mantle. The upper mantle extends from the crust, mantle boundary down to a depth of about 660 kilometers. The upper mantle can be divided into 3 different parts. The top portion of the upper mantle is part of the stronger lithosphere, and beneath that is the weaker asthenosphere. The bottom part of the upper mantle is called the transition zone. The lithosphere consists of the entire crust plus the uppermost mantle and forms Earth's relatively cool, rigid outer shell. Averaging about 100 kilometers thick, the lithosphere is more than 250 kilometers thick below the oldest portions of the continents. Beneath this rigid layer to a depth of about 410 kilometers lies a comparatively weak layer known as the asthenosphere. The top portion of the asthenosphere has a temperature-pressure regime that results in a small amount of melting. Within this very weak zone, the lithosphere is mechanically detached from the layer below. The result is that the lithosphere is able to move independently of the asthenosphere, a fact we will consider in the next chapter. Did you know? Geologists have never sampled the mantle or core directly, so how did we learn about the composition and structure of Earth's interior? The structure of Earth's interior is determined by analyzing seismic waves from earthquakes. As these waves of energy penetrate Earth's interior, they change speed and are bent and reflected as they move through zones having different properties. Monitoring stations around the world detect and record this energy. There is more about this in Chapter 9. It is important to emphasize that the strength of various Earth materials is a function of both their composition and the temperature and pressure of their environment. You should not get the idea that the entire lithosphere behaves like a rigid or brittle solid similar to rocks found on the surface. Rather, the rocks of the lithosphere get progressively hotter and weaker with increasing depth. At the depth of the uppermost asthenosphere, the rocks are close enough to their melting temperature that they are very easily deformed. Thus, the uppermost asthenosphere is weak because it is near its melting point, just as hot wax is weaker than cold wax. From about 410 kilometers to about 660 kilometers in depth is the part of the upper mantle called the transition zone. The top of the transition zone is identified by a sudden increase in density from about 3.5 to 3.7 gcm3. This change occurs because minerals in the rock peridotite respond to the increase in pressure by forming new minerals with closely packed atomic structures. The lower mantle. From a depth of 660 kilometers to the top of the core, at a depth of 2,900 kilometers, is the lower mantle. Because of an increase in pressure, the mantle gradually strengthens with depth. Despite their strength, however, the rocks within the lower mantle are very hot and capable of extremely gradual flow. Earth's core. The core is composed of an iron-nickel alloy with minor amounts of oxygen, silicon, and sulfur, elements that readily form compounds with iron. At the extreme pressure found in the core, This iron-rich material has an average density of nearly 11 gcm3 and approaches 14 times the density of water at Earth's center. The core is divided into two regions that exhibit very different mechanical strengths. The outer core is a liquid layer 2,270 kilometers thick. The movement of metallic iron within this zone generates Earth's magnetic field. The inner core is a sphere that has a radius of 1,216 kilometers. Despite its higher temperature, the iron in the inner core is solid due to the immense pressures that exist in the center of the planet. Concept checks 1.6. 1. List and describe the three major layers defined by their chemical composition. 2. Contrast the lithosphere and asthenosphere. 3. Distinguish between the outer core and the inner core. 1.7 Rocks and the rock cycle. Sketch, label, and explain the rock cycle. Rock is the most common and abundant material on Earth. To a curious traveler, the variety seems nearly endless. When a rock is examined closely, we find that it usually consists of smaller crystals called minerals. Minerals are chemical compounds, each with its own composition and physical properties. The grains or crystals may be microscopically small or easily seen with the unaided eye. The minerals that compose a rock strongly influence its nature and appearance. In addition, a rock's texture, the size, shape, and/or arrangement of its constituent minerals, also has a significant effect on its appearance. A rock's mineral composition and texture, in turn, reflect the geologic processes that created it. Such analyses are critical to an understanding of our planet. This understanding has many practical applications, as in the search for energy in mineral resources and the solution of environmental problems. Texture and mineral composition are basic rock features. These two samples are the common igneous rocks granite A and basalt B. Figure 1.21 Full alternative text description. Geologists divide rocks into three major groups: igneous, sedimentary, and metamorphic. Figure 1.22 provides some examples. As you will learn, each group is linked to the others by the processes that act upon and within the planet. Figure 1.21 Two basic rock characteristics. Figure 1.22 Three rock groups. Geologists divide rocks into three groups: igneous, sedimentary, and metamorphic. Figure 1.22 Full alternative text description. Earlier in this chapter, you learned that Earth is a system. This means that our planet consists of many interacting parts that form a complex whole. Nowhere is this idea better illustrated than in the rock cycle. The rock cycle allows us to view many of the interrelationships among different parts of the Earth system. It helps us understand the origin of igneous, sedimentary, and metamorphic rocks and to see that each type is linked to the others by external and internal processes that act upon and within the planet. Consider the rock cycle to be a simplified but useful overview of physical geology. Learn the rock cycle well, you will be examining its interrelationships in greater detail throughout this textbook. The rock cycle helps us understand the origin of the three basic rock groups. Arrows represent processes that link each group to the others. Smart Figure 1.23 The rock cycle. Smart Figure 1.23 Full alternative text description. Watch tutorial, The rock cycle. The basic cycle. Magma is molten rock that forms deep beneath Earth's surface. Over time, magma cools and solidifies. This process, called crystallization, may occur either beneath the surface or, following a volcanic eruption, at the surface. In either situation, the resulting rocks are called igneous rocks. If igneous rocks are exposed at the surface, they undergo weathering, in which the day-in and day-out influences of the atmosphere slowly disintegrate and decompose rocks. The materials that result are often moved downslope by gravity before being picked up and transported by any of a number of erosional agents, such as rivers, glaciers, wind, or waves. Eventually these particles and dissolved substances, called sediment, are deposited. Although most sediment ultimately comes to rest in the ocean, other sites of deposition include river floodplains, desert basins, swamps, and sand dunes. Next, the sediments undergo lithification, a term meaning conversion into rock. Sediment is usually lithified into sedimentary rock when compacted by the weight of overlying layers or when cemented as percolating groundwater fills the pores with mineral matter. If the resulting sedimentary rock is buried deep within earth and involved in the dynamics of mountain building or intruded by a mass of magma, it is subjected to great pressures and/or intense heat. The sedimentary rock reacts to the changing environment and turns into the third rock type, metamorphic rock. When metamorphic rock is subjected to additional pressure changes or to still higher temperatures, it melts, creating magma, which eventually crystallizes into igneous rock, starting the cycle all over again. Where does the energy that drives Earth's rock cycle come from? Processes driven by heat from Earth's interior are responsible for creating igneous and metamorphic rocks. Weathering and erosion, external processes powered by energy from the sun, produce the sediment from which sedimentary rocks form. Alternative paths. The paths shown in the basic cycle are not the only ones that are possible. To the contrary, other paths are just as likely to be followed as those described in the preceding section. These alternatives are indicated by the light blue arrows in Figure 1.23. Rather than being exposed to weathering and erosion at Earth's surface, igneous rocks may remain deeply buried. Eventually these masses may be subjected to the strong compressional forces and high temperatures associated with mountain building. When this occurs, they are transformed directly into metamorphic rocks. Metamorphic and sedimentary rocks, as well as sediment, do not always remain buried. Rather, overlying layers may be stripped away, exposing the once buried rock. When this happens, the material is attacked by weathering processes and turned into new raw materials for sedimentary rocks. Although rocks may seem to be unchanging masses, the rock cycle shows that they are not. The changes, however, take time, great amounts of time. We can observe different parts of the cycle operating all over the world. Today new magma is forming beneath the island of Hawaii. When it erupts at the surface, the lava flows add to the size of the island. Meanwhile, the Colorado Rockies are gradually being worn down by weathering and erosion. Some of this weathered debris will eventually be carried to the Gulf of Mexico, where it will add to the already substantial mass of sediment that has accumulated there. Concept checks 1.7. 1. List 2 rock characteristics that are used to determine the processes that created a rock. 2. Sketch and label a basic rock cycle. Make sure to include alternate paths. 1.8 The face of Earth. List and describe the major features of the continents and ocean basins. The two principal divisions of Earth's surface are the ocean basins and the continents. A significant difference between these two areas is their relative elevation. This difference results primarily from differences in their respective densities and thicknesses, major surface features of the geosphere. Figure 1.24 The face of Earth. Figure 1.24 Full alternative text description. Figure 1.24 Full alternative text description. Ocean basins. The average depth of the ocean floor is about 3.8 kilometers below sea level, or about 4.5 kilometers lower than the average elevation of the continents. The basaltic rocks that comprise the oceanic crust average only 7 kilometers thick and have an average density of about 3.0 gcm3. Continents. The continents are remarkably flat features that have the appearance of plateaus protruding above sea level. With an average elevation of about 0.8 kilometer, continental blocks lie close to sea level, except for limited areas of mountainous terrain. Recall that the continents average about 35 kilometers thick and are composed of granitic rocks that have a density of about 2.7 g/cm3. The thicker and less dense continental crust is more buoyant than the oceanic crust. As a result, continental crust floats on top of the deformable rocks of the mantle at a higher level than oceanic crust for the same reason that a large, empty cargo ship rides higher than a small, loaded. 1. Major features of the ocean floor. If all water were drained from the ocean basins, a great variety of features would be visible, including chains of volcanoes, deep canyons, plateaus, and large expanses of monotonously flat plains. In fact, the scenery would be nearly as diverse as that on the continents. Did you know? Ocean depths are often expressed in fathoms. 1 fathom equals 1.8 m or 6 feet, which is about the distance of a person's outstretched arms. The term is derived from how depth-sounding lines were brought back on board a vessel by hand. As the line was hauled in, a worker counted the number of arm lengths collected. By knowing the length of the person's outstretched arms, the amount of line taken in could be calculated. The length of 1 fathom was later standardized to 6 feet. During the past 70 years, oceanographers have used modern depth-sounding equipment and satellite technology to map significant portions of the ocean floor. These studies have led them to identify 3 major regions: continental margins, deep ocean basins, and oceanic ridges. Continental margin. The continental margin is the portion of the seafloor adjacent to major landmasses. It may include the continental shelf, the continental slope, and the continental rise. Although land and sea meet at the shoreline, this is not the boundary between the continents and the ocean basins. Rather, along most coasts, a gently sloping platform, called the continental shelf, extends seaward from the shore. Because it is underlain by continental crust, it is clearly a flooded extension of the continents. A glance at Figure 1.24 shows that the width of the continental shelf is variable. For example, it is broad along the east and Gulf coasts of the United States but relatively narrow along the Pacific margin of the continent. The boundary between the continents and the deep ocean basins lies along the continental slope, which is a relatively steep drop-off that extends from the outer edge of the continental shelf, called the shelf break, to the floor of the deep ocean. Using this as the dividing line, we find that about 60% of Earth's surface is represented by ocean basins and the remaining 40% by continents. In regions where trenches do not exist, the steep continental slope merges into a more gradual incline known as the continental rise. The continental rise consists of a thick wedge of sediment at moved downslope from the continental shelf and accumulated on the deep ocean floor. Deep ocean basins. Between the continental margins and oceanic ridges are deep ocean basins. Parts of these regions consist of incredibly flat features called abyssal plains. The ocean floor also contains extremely deep depressions that are occasionally more than 11,000 meters deep. Although these deep ocean trenches are relatively narrow and represent only a small fraction of the ocean floor, they are nevertheless very significant features. Some trenches are located adjacent to young mountains that flank the continents. For example, in Figure 1.24 the Peru-Chile Trench off the west coast of South America parallels the Andes Mountains. Other trenches parallel island chains called volcanic island arcs. Dotting the ocean floor are submerged volcanic structures called seamounts, which sometimes form long, narrow chains. Volcanic activity has also produced several large lava plateaus, such as the Ontong Java Plateau located northeast of New Guinea. In addition, some submerged plateaus are composed of continental-type crust. Examples include the Campbell Plateau southeast of New Zealand and the Seychelles Bank northeast of Madagascar. Oceanic ridges. The most prominent feature on the ocean floor is the oceanic ridge, or mid-ocean ridge. As shown in Figure 1.24, the Mid-Atlantic Ridge and the East Pacific Rise are parts of this system. This broad elevated feature forms a continuous belt that winds for more than 70,000 kilometers around the globe, in a manner similar to the seam of a baseball. Rather than consist of highly deformed rock, such as most of the mountains on the continents, the oceanic ridge system consists of layer upon layer of igneous rock that has been fractured and uplifted. Being familiar with the topographic features that comprise the face of Earth is essential to understanding the mechanisms that have shaped our planet. What is the significance of the enormous ridge system that extends through all the world's oceans? What is the connection, if any, between young, active mountain belts and oceanic trenches? What forces crumple rocks to produce majestic mountain ranges? These are a few of the questions that will be addressed in the next chapter. As we begin to investigate the dynamic processes that shaped our planet in the geologic past and will continue to shape it in the future. Major features of the continents. The major features of the continents can be grouped into two distinct categories: uplifted regions of deformed rocks that make up present-day mountain belts and extensive flat, stable areas that have eroded nearly to sea level. Notice in Figure 1.25 that the young mountain belts tend to be long, narrow features at the margins of continents and that the flat, stable areas are typically located in the interior of the continents. Distribution of mountain belts, stable platforms, and shields. Smart Figure 1.25 The continents. Smart Figure 1.25 Full alternative text description. Mountain belts. The most prominent features of the continents are mountains. Although the distribution of mountains appears to be random, this is not the case. The youngest mountains are located principally in two major zones. The Circum-Pacific Belt includes the mountains of the Western Americas and continues into the Western Pacific, in the form of volcanic island arcs. Island arcs are active mountainous regions composed largely of volcanic rocks and deformed sedimentary rocks. Examples include the Aleutian Islands, Japan, the Philippines, and New Guinea. Watch tutorial: Shields, Platforms, and Mountains. The other major mountain belt extends eastward from the Alps through Iran and the Himalayas and then dips southward into Indonesia. Careful examination of mountainous terrains reveals that most are places where thick sequences of rocks have been squeezed and highly deformed, as if placed in a gigantic vise. Older mountains are also found on the continents. Examples include the Appalachians in the eastern United States and the Urals in Russia. Their once lofty peaks are now worn low, as a result of millions of years of weathering and erosion. The stable interior. Unlike the young mountain belts, which have formed within the past 100 million years, the interiors of the continents, called cratons, have been relatively stable for the past 600 million years or even longer. Typically these regions were involved in mountain building episodes much earlier in Earth's history. Within the stable interiors are areas known as shields, which are expansive, flat regions composed largely of deformed igneous and metamorphic rocks. Notice in Figure 1.25 that the Canadian Shield is exposed in much of the northeastern part of North America. Radiometric dating of various shields has revealed that they are truly ancient regions. All contain Precambrian age rocks that are more than 1 billion years old, with some samples approaching 4 billion years in age. Even these oldest known rocks exhibit evidence of enormous forces that have folded, faulted, and metamorphosed them. Thus, we conclude that these rocks were once part of an ancient mountain system that has since been eroded away to produce these expansive, flat regions. In other flat areas of the craton, highly deformed rocks, like those found in the shields, are covered by a relatively thin veneer of sedimentary rocks. These areas are called stable platforms. The sedimentary rocks in stable platforms are nearly horizontal, except where they have been warped to form large basins or domes. In North America, a major portion of the stable platform is located between the Canadian Shield and the Rocky Mountains. Concept checks 1.8. 1. Compare and contrast continents and ocean basins. 2. Name the 3 major regions of the ocean floor. What are some features associated with each? 3. Describe the general distribution of Earth's youngest mountains. 4. What is the difference between shields and stable platforms? Concepts in review, an introduction to geology. 1.1 Geology, the science of Earth. Distinguish between physical and historical geology and describe the connections between people and geology. Key terms: geology, physical geology, historical geology. Geologists study Earth. Physical geologists focus on the processes by which Earth operates and the materials that result from those processes. Historical geologists apply an understanding of Earth materials and processes to reconstruct the history of our planet. People have a relationship with planet Earth that can be positive and negative. Earth processes and products sustain us every day, but they can also harm us. Similarly, people have the ability to alter or harm natural systems, including those that sustain civilization. 1.2 The development of geology. Summarize early and modern views on how change occurs on Earth and relate them to the prevailing ideas about the age of Earth. Key terms: catastrophism, uniformitarianism. Early ideas about the nature of Earth were based on religious traditions and notions of great catastrophes. In 1795, James Hutton emphasized that the same slow processes have acted over great spans of time and are responsible for Earth's rocks, mountains, and landforms. This similarity of process over vast spans of time led to this principle being dubbed uniformitarianism. Based on the rate of radioactive decay of certain elements, the age of Earth has been calculated to be about 4,600,000,000 years. That is an incredibly vast amount of time. In what eon, era, period, and epoch do we live? 1.3 The nature of scientific inquiry. Discuss the nature of scientific inquiry, including the construction of hypotheses and the development of theories. Key terms: hypothesis theory, scientific method. Geologists make observations, construct tentative explanations for those observations, and then test those hypotheses with field investigations and laboratory work. In science, a theory is a well-tested and widely accepted view that the scientific community agrees best explains certain observable facts. As flawed hypotheses are discarded, scientific knowledge moves closer to a correct understanding, but we can never be fully confident that we know all the answers. Scientists must always be open to new information that forces changes in our model of the world. 1.4 Earth as a system. List and describe Earth's 4 major spheres. Define system and explain why Earth is considered to be a system. Key terms: hydrosphere, atmosphere, biosphere, geosphere. Earth system, science system. Earth's physical environment is traditionally divided into 3 major parts: the solid Earth, called the geosphere, the water portion of our planet, called the hydrosphere, and Earth's gaseous envelope, called the atmosphere. A 4th Earth sphere is the biosphere, the totality of life on Earth. It is concentrated in a relatively thin zone that extends a few kilometers into the hydrosphere and geosphere and a few kilometers up into the atmosphere. Of all the water on Earth, more than 96% is in the oceans, which cover nearly 71% of the planet's surface. Although each of Earth's 4 spheres can be studied separately, they are all related in a complex and continuously interacting whole that is called the Earth system. Earth system science uses an interdisciplinary approach to integrate the knowledge of several academic fields in the study of our planet and its global environmental problems. The 2 sources of energy that power the Earth system are the Sun, which drives the external processes that occur in the atmosphere, hydrosphere, and at Earth's surface, and heat from Earth's interior that powers the internal processes that produce volcanoes, earthquakes, and mountains. Is glacial ice part of the geosphere, or does it belong to the hydrosphere? Explain your answer. 1.5 Origin and early evolution of Earth. Outline the stages in the formation of our solar system. Key terms. Nebular theory. Solar nebula. The nebular theory describes the formation of the solar system. The planets and Sun began forming about 5 billion years ago from a large cloud of dust and gases. As the cloud contracted, it began to rotate and assume a disk shape. Material that was gravitationally pulled toward the center became the protosun. Within the rotating disk, small centers, called planetesimals, swept up more and more of the cloud's debris. Because of their high temperatures and weak gravitational fields, the inner planets were unable to accumulate and retain many of the lighter components. Because of the very cold temperatures far from the Sun, the large outer planets consist of huge amounts of lighter materials. These gaseous substances account for the comparatively large sizes and low densities of the outer planets. Earth is about 4.6 billion years old. If all of the planets in our solar system formed at about the same time, how old would you expect Mars to be? Jupiter? The Sun? 1.6 Earth's internal structure. Describe Earth's internal structure. Key terms. Crust mantle lithosphere asthenosphere transition zone lower mantle core outer core inner core. Compositionally, the solid Earth has three layers: core, mantle, and crust. The core is most dense, and the crust is least dense. Earth's interior can also be divided into layers based on physical properties. The crust and upper mantle make a two-part layer called the lithosphere, which is broken into the plates of plate tectonics. Beneath that is the weak asthenosphere. The lower mantle is stronger than the asthenosphere and overlies the molten outer core. This liquid is made of the same iron, nickel alloy as the inner core, but the extremely high pressure of Earth's center compacts the inner core into a solid form. The diagram represents Earth's layered structure. Does it show layering based on physical properties or layering based on composition? Identify the lettered layers. Figure 1.10 to 1 full alternative text description. 1.7 Rocks and the rock cycle. Sketch, label, and explain the rock cycle. Key terms. Rock cycle: igneous rock, sediment, sedimentary rock, metamorphic rock. The rock cycle is a good model for thinking about the transformation of one rock to another due to earth processes. All igneous rocks are made from molten rock. All sedimentary rocks are made from weathered products of other rocks. All metamorphic rocks are the products of pre-existing rocks that are transformed at high temperatures or pressures. Given the right conditions, any kind of rock can be transformed into any other kind of rock. Name the processes that are represented by each of the letters in this simplified rock cycle diagram. Figure 1.10 to 1 full alternative text description. 1.8 The face of Earth. List and describe the major features of the continents and ocean basins. Key terms. Ocean basin: continent, continental margin. Continental shelf, continental slope, continental rise, deep ocean basin, abyssal plain, deep ocean trench, seamount. Oceanic ridge, mountain belt, craton, shield, stable platform. Two principal divisions of Earth's surface are the continents and ocean basins. A significant difference is their relative elevations, which results primarily from differences in their respective densities and thicknesses. Continents consist of relatively flat, stable areas called cratons. Where a craton is blanketed by a relatively thin layer of sediment or sedimentary rock, it is called a stable platform. Where a craton is exposed at the surface, it is known as a shield. Wrapping around the edges of some cratons are mountain belts, linear zones of intense deformation and metamorphism. Shallow portions of the oceans are essentially flooded margins of the continents, and deeper portions include vast abyssal plains and deep ocean trenches. Seamounts and lava plateaus interrupt the abyssal plain in some places. Put these features of the ocean floor in order from shallowest to deepest: continental slope, deep ocean trench, continental shelf, abyssal plain, and continental rise. Give it some thought. 1. The length of recorded history for humankind is about 5,000 years. Clearly, most people view this span as being very long. How does it compare to the length of geologic time? Calculate the percentage or fraction of geologic time that is represented by recorded history. To make calculations easier, round the age of Earth to the nearest billion. 2. After entering a dark room, you turn on a wall switch, but the light does not come on. Suggest at least 3 hypotheses that might explain this observation. Once you have formulated your hypotheses, what is the next logical step? 3. Refer to the graph in Figure 1.13 to answer the following questions. A. If you were to climb to the top of Mount Everest, how many breaths of air would you have to take at that altitude to equal the amount of air in one breath at sea level? B. If you are flying in a commercial jet at an altitude of 12 kilometers, about what percentage of the atmosphere's mass is below you? 4. Making accurate measurements and observations is a basic part of scientific inquiry. Identify 2 images in this chapter that illustrate a way in which scientific data are gathered. Suggest an advantage that might be associated with the examples you select. 5. The accompanying photo provides an example of interactions among different parts of the Earth system. It is a view of a debris flow that was triggered by extraordinary rains in January 2005. Describe how each of Earth's 4 spheres was influenced and/or involved in this natural disaster that buried a portion of La Conchita, California. 6. Refer to Figure 1.23. How does the rock cycle diagram, particularly the process arrows, support the fact that sedimentary rock is the most abundant rock type on the surface of Earth? 7. This photo shows the picturesque coastal bluffs and rocky shoreline along a portion of the California coast south of San Simeon State Park. This area, like other shorelines, is described as an interface. What does this mean? Does the shoreline represent the boundary between the continent and ocean basin? Explain. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 2: Plate Tectonics, A Scientific Revolution Unfolds. Hikers crossing a crevasse in Khumbu Glacier, Mount Everest, Nepal. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 2.1 Summarize the view that most geologists held prior to the 1960s regarding the geographic positions of the ocean basins and continents. 2.2 List and explain the evidence Wegener presented to support his continental drift hypothesis. 2.3 List the major differences between Earth's lithosphere and asthenosphere and explain the importance of each in the plate tectonics theory. 2.4 Sketch and describe the movement along a divergent plate boundary that results in the formation of new oceanic lithosphere. 2.5 Compare and contrast the 3 types of convergent plate boundaries and name a location where each type can be found. 2.6 Describe the relative motion along a transform fault boundary and locate several examples of transform faults on a plate boundary map. 2.7 Explain why plates such as the African and Antarctic plates are increasing in size, while the Pacific plate is decreasing in size. 2.8 List and explain the evidence used to support the plate tectonics theory. 2.9 Describe 2 methods researchers use to measure relative plate motion. 2.10 Describe plate, mantle convection and explain two of the primary driving forces of plate motion. Plate tectonics is the first theory to provide a comprehensive view of the processes that produced Earth's major surface features, including the continents and ocean basins. Within the framework of this model, geologists have found explanations for the basic causes and distribution of earthquakes, volcanoes, and mountain belts. Further, the plate tectonics theory helps explain the formation and distribution of igneous and metamorphic rocks and their relationship with the rock cycle. 2.1 From continental drift to plate tectonics. Summarize the view that most geologists held prior to the 1960s regarding the geographic positions of the ocean basins and continents. Until the late 1960s, most geologists held the view that the ocean basins and continents had fixed geographic positions and were of great antiquity. Over the following decade, scientists came to realize that Earth's continents are not static. Instead, they gradually migrate across the globe. These movements cause blocks of continental material to collide, deforming the intervening crust and thereby creating Earth's great mountain chains. Furthermore, land masses occasionally split apart. As continental blocks separate, a new ocean basin emerges between them. Meanwhile, other portions of the seafloor plunge into the mantle. In short, a dramatically different model of Earth's tectonic processes emerged. Tectonic processes are processes that deform Earth's crust to create major structural features, such as mountains, continents, and ocean basins. The tallest mountains on Earth, the Himalayas, were created when the subcontinent of India collided with southeastern Asia. Figure 2.1 Himalayan mountain range as seen from northern India. This profound reversal in scientific thought has been appropriately called a scientific revolution. The revolution began early in the 20th century as a relatively straightforward proposal termed continental drift. For more than 50 years, the scientific community categorically rejected the idea that continents are capable of movement. North American geologists in particular had difficulty accepting continental drift, perhaps because much of the supporting evidence had been gathered from Africa, South America, and Australia, continents with which most North American geologists were unfamiliar. After World War II, modern instruments replaced rock hammers as the tools of choice for many Earth scientists. Armed with more advanced tools, geologists and a new breed of researchers, including geophysicists and geochemists, made several surprising discoveries that rekindled interest in the drift hypothesis. By 1968, these developments had led to the unfolding of a far more encompassing explanation known as the theory of plate tectonics. In this chapter, we will examine the events that led to this dramatic reversal of scientific opinion. We will also briefly trace the development of the continental drift hypothesis, examine why it was initially rejected, and consider the evidence that finally led to the acceptance of its direct descendant, the theory of plate tectonics. Did you know? Alfred Wegener, best known for his continental drift hypothesis, also wrote numerous scientific papers on weather and climate. Following his interest in meteorology, Wegener made 4 extended trips to the Greenland ice sheet to study its harsh winter weather. In November 1930, while making a month-long trek across the ice sheet, Wegener and a companion perished. Concept checks 2.1. 1. Briefly describe the view held by most geologists prior to the 1960s regarding the ocean basins and continents. 2. What group of geologists were the least receptive to the continental drift hypothesis, and why? 2.2 Continental drift, an idea before its time. List and explain the evidence Wegener presented to support his continental drift hypothesis. During the 1600s, as better world maps became available, people noticed that continents, particularly South America and Africa, could be fit together like pieces of a jigsaw puzzle. However, little significance was given to this observation until 1915, when Alfred Wegener, a German meteorologist and geophysicist, wrote The Origin of Continents and Oceans. This book outlined Wegener's hypothesis, called continental drift, which dared to challenge the long-held assumption that the continents and ocean basins had fixed geographic positions. Wegener suggested that a single supercontinent consisting of all Earth's land masses once existed. He named this giant landmass Pangaea. Wegener further hypothesized that about 200 million years ago, during a time period called the Mesozoic era, this supercontinent began to fragment into smaller landmasses. These continental blocks then drifted to their present positions over a span of millions of years. The supercontinent of Pangaea, as it is thought to have formed in the late Paleozoic and early Mesozoic eras more than 200 million years ago. Smart Figure 2.2 Reconstructions of Pangaea. Smart Figure 2.2 Full alternative text description. Wegener and others who advocated the continental drift hypothesis collected substantial evidence to support their point of view. The fit of South America and Africa and the geographic distribution of fossils and ancient climates all seem to buttress the idea that these now separate land masses had once been joined. Let us examine some of this evidence. Evidence: the continental jigsaw puzzle. Watch tutorial, Pangaea. Like a few others before him, Wegener suspected that the continents might once have been joined when he noticed the remarkable similarity between the coastlines on opposite sides of the Atlantic Ocean. However, other Earth scientists challenged Wegener's use of present-day shorelines to fit these continents together. These opponents correctly argued that wave erosion and depositional processes continually modify shorelines. Even if continental displacement had taken place, a good fit today would be unlikely. Because Wegener's original jigsaw fit of the continents was crude, it is assumed that he was aware of this problem. Scientists later determined that a much better approximation of the outer boundary of a continent is the seaward edge of its continental shelf, which lies submerged a few hundred meters below sea level. In the early 1960s, Sir Edward Bullard and two associates constructed a map that pieced together the edges of the continental shelves of South America and Africa at a depth of about 900 meters. The remarkable fit obtained was more precise than even these researchers had expected. The best fit of South America and Africa occurs along the continental slope at a depth of 500 fathoms. Figure 2.32 of the puzzle pieces. Evidence: fossils matching across the seas. Although the seed for Wegener's hypothesis came from the remarkable similarities of the continental margins on opposite sides of the Atlantic, it was when he learned that identical fossil organisms had been discovered in rocks from both South America and Africa that his pursuit of continental drift became more focused. Wegener learned that most paleontologists agreed that some type of land connection was needed to explain the existence of similar Mesozoic age life forms on widely separated land masses. Just as modern life forms native to North America are not the same as those of Africa and Australia, Mesozoic-era organisms on widely separated continents should have been distinctly different. Mesosaurus. To add credibility to his argument, Wegener documented several cases in which the same fossil organism is found only on land masses that are now widely separated, even though it is unlikely that the living organism could have crossed the barrier of a broad ocean. A classic example is Mesosaurus, a small aquatic freshwater reptile whose fossil remains are limited to rocks of Permian age in eastern South America and southwestern Africa. If Mesosaurus had been able to make the long journey across the South Atlantic, its remains should be more widely distributed. As this is not the case, Wegener asserted that South America and Africa must have been joined during that period of Earth history. Fossils of identical organisms have been discovered in rocks of similar age in Australia, Africa, South America, Antarctica, and India, continents that are currently widely separated by ocean barriers. Wegener accounted for these occurrences by placing these continents in their pre-drift locations. Figure 2.4 Fossil evidence supporting continental drift. Figure 2.4 Full alternative text description. How did opponents of continental drift explain the existence of identical fossil organisms in places separated by thousands of kilometers of open ocean? Rafting, transoceanic land bridges, and island stepping stones were the most widely invoked explanations for these migrations. We know, for example, that during the Ice Age that ended about 8,000 years ago, the lowering of sea level allowed mammals to cross the narrow Bering Strait that separates Russia and Alaska. Was it possible that land bridges once connected Africa and South America but later subsided below sea level? Modern maps of the seafloor substantiate Wegener's views and show no such sunken land bridges. These sketches illustrate various early proposals to explain the occurrence of similar species on landmasses now separated by vast oceans. Figure 2.5 How do land animals cross vast oceans? Figure 2.5 Full alternative text description. Glossopteris. Wegener also cited the distribution of the fossil, seed fern, Glossopteris as evidence for Pangaea's existence. With tongue-shaped leaves and seeds too large to be carried by the wind, this plant was known to be widely dispersed throughout Africa, Australia, India, and South America. Later, fossil remains of Glossopteris were also discovered in Antarctica. Wegener also learned that these seed ferns and associated flora grew only in cool climates, similar to central Canada. Therefore, he concluded that when these landmasses were joined, they were located much closer to the South Pole. In 1912, Captain Robert Scott and two companions froze to death lying beside 16 kilograms of rock on their return from a failed attempt to be the first to reach the South Pole. These samples, collected on Beardmore Glacier, contained fossil remains of Glossopteris. Evidence, rock types and geologic features. You know that successfully completing a jigsaw puzzle requires maintaining the continuity of the picture while fitting the pieces together. In the case of continental drift, this means that the rocks on either side of the Atlantic that predate the proposed Mesozoic split should match up to form a continuous picture when the continents are fitted together as Wegener proposed. Indeed, Wegener found such matches across the Atlantic. For instance, highly deformed igneous rocks in Brazil closely resemble similar rocks of the same age in Africa. Also, the mountain belt that includes the Appalachians trends northeastward through the eastern United States and disappears off the coast of Newfoundland. Mountains of comparable age and structure are found in the British Isles and Scandinavia. When these landmasses are positioned as Wegener proposed, the mountain chains form a nearly continuous belt. As Wegener wrote, it is just as if we were to refit the torn pieces of a newspaper by matching their edges and then check whether the lines of print run smoothly across. If they do, there is nothing left but to conclude that the pieces were in fact joined in this way. Alfred Wegener, The Origin of Continents and Oceans, translated from the Fourth Revised German edition of 1929 by J. Berman. A. The current locations of the continents surrounding the Atlantic. B. The configuration of the continents about 200 million years ago. Figure 2.6 Full alternative text description. Evidence, ancient climates. Figure 2.6 Matching mountain ranges across the North Atlantic. Because Alfred Wegener was a student of world climates, he suspected that paleoclimatic data might also support the idea of mobile continents. His assertion was bolstered by the discovery of evidence for a glacial period dating to the late Paleozoic era in southern Africa, South America, Australia, and India. This meant that about 300 million years ago, vast ice sheets covered extensive portions of the southern hemisphere as well as India. Much of the land area that contains evidence of this Paleozoic glaciation presently lies within 30 degrees of the equator, in subtropical or tropical climates. How could extensive ice sheets form near the equator? One proposal suggested that our planet experienced a period of extreme global cooling. Wegener rejected this explanation because during the same span of geologic time, large tropical swamps existed in several locations in the northern hemisphere. The lush vegetation in those swamps was eventually buried and converted to coal. Today these deposits comprise major coal fields in the eastern United States and northern Europe. Many of the fossils found in these coal-bearing rocks were produced by tree ferns with large fronds, ferns that would have grown in warm, moist climates. The existence of these large tropical swamps, Wegener argued, was inconsistent with the proposal that extreme global cooling caused glaciers to form in areas that are currently tropical. Figure 2.7 Paleoclimatic evidence for continental drift. About 300 million years ago, ice sheets covered extensive areas of the southern hemisphere and India. Arrows show the direction of ice movement that can be inferred from the pattern of glacial scratches and grooves found in the bedrock. Tropical coal swamps also existed in areas that are